Yeah, Assalamualaikum and good evening. So we continue our discussion on our tutorial here. So I think we stopped at question 1.10 last week. So we continue with 1.11 today. So I think you already have the PDF version of this textbook and you have all the questions behind each chapter. So I can go a little bit faster here. So let's say for 1.11 here, so estimate the viscosity of nitrogen at 66 megapascal and 49 degrees Celsius and compare with the measure value of 45 micropascal second. So and then we have this table from the textbook. So and then we could solve this by using this idea. So from the table, we know that the nitrogen has the critical temperature of 227 degree R, and the critical pressure is 33.5 atmospheric. So critical viscosity is 1.8 by the power of 10 minus 5 Pascal seconds. And then the degree R here is actually the Rankine unit. So we could convert it into Kelvin by using this equation. And for 227 degree R, so it is equal to 126.11 Kelvin. And then we could calculate the reduced temperature by using this equation. So it's become 2.553 Kelvin. So and then we could convert the ATM unit here. So to Pascal unit, we know that 1 ATM or 1 atmospheric pressure is equal to 101 kilopascal. So if 33.5, so we have around these numbers. And then we calculate the reduced pressure. PR it can be calculated as here. So all the equation here is in the textbook, I think. So and then we know here the reduced temperature and the reduced pressure can be estimated by using this table. So by looking at TR is equal to 2.553. So this is between 2 and 3 here. So this is in log unit, I think. So you can assume that 2.5 is around in the middle here. So if we take care about this, so and then we use the PR here of 25. So I think we need to refer of this line here, and then we could assume it is around 2.5 for the reduced kinematic viscosity here. So we know that the mu r here is equal to 0.5, and the equation is mu over mu c, the critical viscosity. So we substitute the value, we could estimate the value of dynamic viscosity is equal to 45 micropascal a second. So this is question 1.12. So the idea is to estimate the thermal conductivity of air at 400 degrees Celsius and 1 atm, and compare with the measured value of 0.05015 watt per meter Kelvin. So this table is the property of air at 1 atmospheric pressure. So you may have this from any fluid mechanics textbook. So and then again, if you refer to the table A5, so the critical temperature is around 238 degree Rankine, degree R. So it is equal to 132.2 Kelvin. So the temperature is 400 degrees Celsius, which is 673 Kelvin. So from here we could compare that the temperature is greater than the critical temperature. So the PATM is equal to 1, and it is far lower compared to the critical pressure, which is 36.4 ATM. So because of this condition, so according to the textbook, we could categorize this one as the low density. So and then we could use the use of power law estimation as stated in the equation here. So the equation is of this one. So and then we need to use correct value for each element. So for an air, so the T naught and K naught is already in the table, and the value of N is actually equal to 0.81. So and then we substitute with all the parameters here, we could get that K is equal to 0.05005. So and then so we could compare the value given in the question. So it is found that the error is around 0.2%. Okay, so for question 1.13 here, so we need to estimate the viscosity and also the thermal conductivity of this mixture. So the question is, it is desired to form a gas mixture of 23% of carbon dioxide, 40% of oxygen, and 63% of nitrogen at 1 atmospheric and 20 degrees Celsius. So we need to estimate the viscosity and thermal conductivity of this mixture. So for liquid, actually, we could measure it. We could measure it by using the rotational viscometer, and then we could get the value of dynamic viscosity. But for gas, it is quite difficult to measure it. So normally we will use the pure gas, the viscosity of pure gas, and then we estimate when this gas is mixed together. So this is the common value of carbon dioxide, oxygen, and nitrogen. So we know its molecular mass, which is 44, 32, and 28 respectively. And then this is the mole fraction. So the mole fraction is reflect to the percentage of the gas here. So and then the mu here, the dynamic viscosity for each gas is quite common value. So you could get from any textbooks, you can get from any tables. Okay, but the problem now, if what happened if these three gas mix together, for sure the viscosity change. So this is the common value that we can get from the textbooks, and this is also the thermal conductivity of the for each gases. Okay, so estimate the mixture viscosity. We could use equation 1.54. So you can get this equation from the textbooks. Okay, the idea is we have a mu, means the dynamic viscosity for the mixture, by using the idea of sigma of x mu over total of x phi here, and the amount of phi here is mentioned in this equation. So which is the m here is the molecular weight, and the x here is the mole fraction. So this is the mole fraction here. So the mu here is the dynamic viscosity. So and then the idea of this one is I would like to show here is how to solve this one. So I think by looking at the equation, you have experience of solving this kind of equation. So what you need to do is actually, first we need to build a table here. So we have carbon dioxide, we have an oxygen, and then we have nitrogen here, and then this also, okay, carbon dioxide, oxygen, and nitrogen. So let's say we have, we assume it is 1, 2, and 3. This is also 1, 2, and 3. And then we need to calculate each phi for each combination. So mean the 1 here, so every 1 here and 1 here, and 1 2 here is 1 here and 2 at here, 1, 3 here means you need to use the parameter of carbon dioxide, and then you need to mix with the nitrogen here. So the example of calculation is like this. So I just give you this one. I think you could compare this one. For example, if for the calculation 1 here, we are comparing the value of carbon dioxide and carbon dioxide here. So that's why we get when we have both I and J here is I and J here is the same element. So for sure we will get 1. So that's why we get 1 here. So you could assume that this blue color is actually the parameter of J, and this orange color is the parameter of I. So and then all this value is actually is the value when you calculate like this. So for example, for calculate 1, 2 here, so we just use the I here is the 1.37. So I here, so you have to use 1.37 here. So I mean it is the mu of carbon dioxide. So and then here is 1.92 because it is number 2. So it is the amount of oxygen, because we are going to solve in the 1, 2 column here. Okay, so I hope you could snap these notes, because later on you can do by yourself the calculation of this one. So we calculate everything. So this is the example for phi11, phi12, and phi13. So we get it is around 1, 0.72, 0.723 here. So if you see, so we have 0.7269, 0.7234. So and then we need to repeat the calculation again for phi 21, 22, 23, and also the rest of this one. So then if you get this table from the this kind of calculation, so what you need to do is we need to solve these terms only. So this term means the sigma here means the summation of the or the total one. So we have xj here. So xj mean x1, for example. Then we need to get some x1, phi11, x plus x2, phi12, and x3, phi13. Okay, so and then we calculate all of these, and then we have of these, and then we add everything here. So then we could conclude that the total overall value of this one is 0.786, 1.0958, and 1.0858. So and then and finally we could calculate the dynamic viscosity of this mixture in estimation like this. So all this parameter is actually reflect the equation of this one. Okay, so and then we have I here, and the sigma here means the total, the summation. So this is the summation. So and then we calculate for I and J. So we have this is everything for I mean for carbon dioxide. So this is for oxygen, and this is for nitrogen. So finally we add all this value, and we could assume that it is might be this case. This is around 1.608 times 10 by the power of -5 Pascal second. So actually this is the step for the upper estimation of viscosity. So and then if we want to calculate the conductivity K, we could use the same method, but make sure that you use the same the equation for conductivity. So we have the equation for conductivity here is shown in this slide. So and then this is the equation for phi here. So and then if you do the same thing, so mean we create table there, we put all the we assume that this row is J and this column is I, and then we assume the coordinates or the location. So this is 1, 2, and 3, and then this is also 1, 2, and 3. So and then we could get all these parameter. So to calculate this one, so as I showed you previously, so we could calculate by doing the same way, the same method there. So but you need a little bit details and a little bit patient to calculate all of them. So it is okay for you if you know how to use your scientific calculator to calculate that, but it is might be advantage for you to know the exactly the method to calculate manually. So you get this one, and finally we do the exactly the same method to calculate this one. So finally we get the thermal conductivity of mixture can be estimated as 0.021 watt meter Kelvin as shown here.
Excuse me, Doctor, may I interrupt?
Yes.
Doctor, about the previous question,
Yeah.
113. This equation about mu and k is just related to mixture gases.
Yes.
Yes, this one.
Yes. Okay. The estimation is for gases. For gas.
Okay.
Okay,
Thank you.
for liquid, so it is
Okay.
not worth for us to
Thank
do
you.
the simulation, to do the estimation like this, because if the liquid, if you mix, for example, oil with another oil plus another nanoparticle and so on and so forth, so the best one to know the viscosity is by measure it by the viscometer, because the fluid, because the liquid can be there. Can you get me? Okay, so gas, the problem is if you make a gas and then there is a special way to
Yes,
measure
doctor.
viscosity of gas. That's why, but to measure that one,
Okay.
we need a specific measuring device. So instead of that one, why not we just use the common viscosity value that we can get from any textbook, because this is very common. Then we estimate by using this equation. Okay. Okay, again, we have for question 1.14. So we have some measured value for the viscosity of ammonia gas as follows. So we have temperature 300, 400, 500, 600, 700, and 800. And the viscosity amount is shown in this table. So and then feed this data in the least square error sense to the Sunderland Law as shown below. So in the textbook, there were explanation a little bit about Sunderland Law. So the idea is about this equation. So this is actually you need to plot a graph, but it's okay. I just to show this work. So the equation of mu over mu naught equal T over T naught, which is T naught is equal to 300 based on this table actually, because actually this equation is if you have set of data here, so normally we will pick up our own T naught here. So normally we pick up the lowest one, so we get 300 K there, and then we substitute the one, and then we estimate the value of n. So how to estimate the value of n here? So this is the basic correlation. So we substitute all the value here, and then we could do this by log graph, and then the n here will become the gradient. So the estimation here is actually by plotting a graph. So for example, like this. So if we plot all the graph here, so it is quite a straight line here, and then we assume that it is the the relation of temperature and viscosity here is not it start with 0 0 there. So now the graph here must be start at 0 0, because for viscosity it is very weird if we have the coefficient here of C. So we plot a graph here. So we do the graph, we take the gradient, because the gradient here will show the value of n. And then from the estimation from the Excel, we found it is equal to y equal 1.0451x. So it is equal to y equal mc, y equal mx. So the value of 1.0451 here is the gradient of this graph. So then when we compare with this equation, so we could estimate the value of n here is equal 1.0451. Then we could substitute in this equation, means that next time when we want to estimate the ammonia gas, so we could just substituting into this equation to get the what other value that we need from this equation. So another thing that you could take idea from this one is, if you do master project later on, might be you could change your graph by using the log, because normally when you have data, sometimes your data will give you a curve one. And if sometimes it will help you when you change your data, the axis of your x-axis, the mean you change for x-axis and y-axis into the value of log here. So might be you will get a straight line. Then when you get a straight line, so you have chance to calculate the equation of that straight line, and then you can propose the gradient of that one. And if you see, a lot of researcher had do that, and then they could propose another equation or other relationship between two elements. So this is the hint for you if you conduct master project later on. So you please try to do the log graph to evaluate your result. Okay. So here we are answering a question about the shear stress and force, and then it's for example, we need to analyze the flow between two plates as figure 1.15. Okay, and then by assuming the fluid is a dual power law fluid as in equation 1.31a. So the idea here is actually the liquid is stick very hard on the surface. That's why they call here no slip condition, means that the molecule here is not slipping. It's not slip, means it stick very well on the surface. So if this plate is moving at certain velocity, means that this molecule here will also feel the same velocity as the moving plate here. So, and then we could calculate, we could draw the velocity profile linear like this, because normally the fluid between two plates like this, we assume that the velocity profile is almost linear. So, and then however, we need to might be comes out with a mathematical equation to show the velocity profile here. So, and the question asks to compute the velocity profile of uy with the power n as a parameter. So means that the power n here means we need to estimate the velocity profile as might be exponent, might be linear. Linear mean the power n might be equal to 1. So if n is equal to 2, so means that your velocity profile is now in quadratic. So, and then they ask us to calculate the velocity at the midpoint h over 2. So this is the total height h, and then we need to calculate the velocity at here for n equals 0.5, equal 1.0 and 2.0. Okay, velocity profile. So consider the flow parallel plate is with no acceleration and no pressure gradient. Therefore, the shear stress is constant. Thus, the velocity gradient also in constant. So we assume that velocity gradient or velocity profile is usually given by du dy. And then because we give a very simple assumption here, because means no acceleration and no pressure gradient means no acceleration is we want to say that the velocity is remain in constant. So we have this condition. So we assume that velocity here is remain in one value, because if the velocity is changes, then you have changes of velocity over time, you have acceleration. But if the velocity is remain in constant, so there are no acceleration. So and then there are no pressure gradient, so they're very simple. If the velocity is constant, then the pressure is also constant. That is the very simple Bernoulli equation. So when the velocity increase, so we have the pressure decrease, so the velocity is not changing, so the pressure is not changed. So and then we arrange this one. So we have du over dy equal b, and then du is equal b dy. So we want to get the velocity profile, so we need to integrate both sides. So we integrate this one, so we will get u equal by plus a. So and then we need to substitute with the boundary condition. So boundary condition here is the condition at the boundary. So it's reflect its own situation. So what is the boundary in this situation? So boundary means is the boundary between this fluid with other element. So in this situation, we have 2 points which has the boundary condition. One is here and the other one is here. Because this is the boundary between this fluid and the upper plate, and this is the boundary between this fluid with the lower plate. So and then after we determine the boundary condition here, we need to give a value, because as you know, we have B and A. We have two unknown parameters, so we need two equations to solve this problem. So how we need to get an equation? We need to substitute this equation with 2 points that belong to that lines. So we could substitute with the coordinate of the boundary condition. So the condition is at y equal to 0, the u is equal to 0, and at y equal to h, the u is equal to capital V. So we could see this condition by looking this plate. So here at y equal to 0, so the velocity is remain 0, because this plate is not moving, and this molecule is stick together on this stick on this fixed plate. However, for this plate, so the no slip condition is still occur, and then that why this molecule will feel or will receive the same velocity as the moving plate. So at this condition, we could say that at y equal to h here, the u means the velocity for this molecule is equal to the capital V, which is the same velocity of the moving plate here. So we substitute these two condition. For first, we substitute with y0 and u0 here. We substitute in the equation, we can get a is equal to 0. Then the equation become u is equal by. Okay, because we already proved that a is equal to 0, then in the second equation here, so it is okay for us to eliminate this term of a here, because the a is 0, then we could ignore or we could eliminate the existence of a. So now our question is on the u equal to by, then if the u is equal to capital V, y is equal to h, and then we have B is equal V over H here, so that we could simplify our equation is U V over H Y. So and then we need to calculate the velocity at midpoint here. So U equal V over H Y. So uh, we have Y equal H over 2, and then U equal V over H over 2 here, and then we get velocity is V over 2. So we could get that the velocity of fluid flow at the midpoint is always U is equal to V over 2. Okay. So and then for this one, actually, is for the equation of n is equal 0 0.5, n equal to 1.0. So I think to how to get the value of 0 0.5 and 2.0 here is actually, so you start here. So with b is equal with certain value, b of the power of 0 0.5, or b with the power of 2, and so on and so forth. So because if you do this, you will get a linear. Okay. Yeah, I skip for that one. Okay. So okay, then for question 1.16 here, okay, so we are evaluating the same situation, which is we have two plates here. One is moving and one is fixed, not moving. However, we don't have the no slip condition. So for example, for question 1.16, repeat the analysis of the velocity profile between two plates, figure 1.15, for a Newtonian fluid, but allow for a slip velocity delta U at both walls. So compute the shear stress at both walls. The slip velocity can be assumed as this one. Okay, so this question means that, so for example, if we have this is the moving plate, and this is the fixed plate. Okay. Okay. Previously, in previous question, we say that this molecule will stick very hard on the surface. Then it will create no slip condition. But in this question, we assume that this molecule actually moving at certain velocity here, means that this molecule is actually slip. And this slip, okay, because the resistance, the shear stress is still act on that molecule. So this molecule cannot move as fast as v velocity. It only can move a little bit with certain micro change, or with the small value of velocity. So, and then in this question, it gives us that the value of the slip velocity delta U is equal to L du dy. Okay, so normally the slip velocity amount will be given to make our calculation easier. So and then for the shear stress here, okay, and then it will be given as tau wall equal mu v over h plus 2l. So it also will be given in the question. Okay, so and then the slip condition on the wall of parallel plate, okay, can be simplified as d1. So delta u is equal L du dy at the wall here. So so the idea of the wall here is actually previously in our calculation we will get substitute the value of y equal to 0. So that is the idea of the wall here. So and then we assume that velocity profile is linear. So it is equal to uy equal a plus by. And you know this equation is for a linear motion. So and then you need to understand of this one, because we have two places where the velocity is now x. One is at the bottom plate and one is at the top plate. So here at the bottom is very simple because previously we assumed that velocity at the bottom, because the molecule is stick very hard on the plate, so the velocity is totally zero. Then in this situation, we found that that molecule is moving with certain micro velocity, so we need to add the u for the bottom, u for the molecule at the bottom is equal to 0 plus delta u. Okay, because there is slip on the bottom plate. Okay, and then at the top here, okay, so the u top, okay, if the molecule is stick very hard, so the molecule will feel the same velocity with the moving plate. So if the moving plate is equal to capital U, so the molecule will feel the capital U. However, now the molecule at the top plate here feel, or they have slip on the molecule. So slip on the molecule means that the molecule cannot stick very hard on the surface. So mean if the wall moving at u velocity per second, so the molecule itself also slip on the surface by delta u. Okay, because we assume that the direction of velocity for the wall and the molecule is the same, so we take the relative velocity. That's why we assume that the velocity for the molecule at the top is now equal capital U minus delta U. Okay, you need to imagine that. You need to imagine you have a molecule there, and that molecule is moving, and for sure it's move on the same direction of the moving plate. So that's why we minus will delta U, because we need to calculate the relative velocity. So you have idea of this one. So and then we solve it. So for example, we give the condition for the bottom plate. So mean at y equal to 0. So we have velocity uy means velocity distribution at y equal to 0 is delta uy equal to 0. So then we could, because we assume that the linear, the velocity profile is linear, so we get a plus by and y equal to 0 with L du dy at y equal to 0. So means we substitute the value of y equal to 0 here, and then we have an a is equal to L and b. And for the top plate here, so we have y equal to h. So you could imagine, because the thickness is the h now, so we have y equal to h. So we substitute the same equation. Okay, we have to equal y equal to h, and this is also y equal to h. Okay, okay, I'm sorry. So we substitute everything, y equal to h here, and we substitute y equal to h here. Okay, so and then so if you do this everything, you could find that the uy here is equal a plus by, and it is equal to u in bracket L plus y over 2L plus h. And then we could calculate the shear stress by using the common shear stress equation, which is mu du dy. So we have a mu. So we could get the value of du dy here by this one. So and then the shear stress here will refer to the plate that move at certain velocity. Because if the fixed plate, the shear stress is there, the molecule is there, so but the effect of shear stress uh, is not there. So we take the du dy for the moving plate, so we substitute this one, so we get this is the terms for the shear stress, and then the shear stress for the bottom and top plate here can be calculated in as shown in this slide. Okay, for question 1.19. So from the previous problem, if the temperature, sphere size and velocity remain the same at flow, at what air pressure will the Reynolds number be equal to 10,000? So I think you already know this. So the previous problem is referred to the sphere, which is diameter is 1.4 centimeter. It is 0.014 meter. So the velocity is 18 meter per second. So the temperature is 293 Kelvin, and the mu is the mu of the air, because we have an air flow here. So the mu here can be take for the atmospheric value. Okay, because air here is the mixture of a lot of air, because in atmospheric there is a ratio of hydrogen, nitrogen, argon gas, and so on, so forth. So please take the atmospheric value of the dynamic viscosity. So and then they want the Reynolds number is 10,000. So we have the Reynolds number here. So Re is equal rho Vd over mu. So here again, you need to understand that sometimes you need to a little bit you need to understand what kind of parameter you need to take. Okay, for example, we have a sphere here. So it is okay for us just to take the diameter of the sphere. So then we rearrange this equation. So if the Reynolds number is 10,000, so we could get that the density of air is must be 0.7183 kilogram per meter cube. So and then to calculate the pressure, if it is an ideal gas, so we substitute everything here. We know the temperature, and then we know the gas constant, so which is normally for an air is 287. So please be careful, because the value of R here, the gas constant, is keep changing with the type of gas, because the idea is you need to calculate it by 8,313 over molecular mass. So if for for air, the atmospheric air, so it is fixed with 287. But if the gas is nitrogen or hydrogen, oxygen, and so on, if it is only a one type of gas, so you need to calculate your own gas constant here. Okay, so this is again about the sleep, no sleep condition, and with sleep condition. Okay, let's say we have a solid cylinder of mass, and then its radius is r and the length is l, fall concentrically through a vertical tube of radius r plus delta r, where delta r is very very small compared to the value of radius. So the tube is filled with gas of viscosity mu and mean free path L. So neglect fluid forces on the front and back face of the cylinder, and consider only shear stress in the annular region, assuming a linear velocity profile. Find an analytical expression for the terminal velocity of fall V of the cylinder for no slip and with slip condition. So wait a minute, I plug in with my for this situation. So the idea is, for example, you have a cylinder here. Okay, and then you put it into the hollow cylinder. So I hope you could imagine you have a hollow cylinder, and then you let it fall with certain in natural fall, means the gravity will pull this object, and inside this tube you will have some kind of gas. Okay, and then the idea of neglect fluid forces on the back and front faces here is, as you know, when something falling down like this, so the air will hit the face, the cylinder surface here, and it will create some kind of resistance. So we neglect that one. We just assume the resistance means that the effect of the viscosity of the gas inside this tube on the surface only. So as you know, on the surface, okay, the flow will flow through this narrow channel, narrow gap. So and then because this cylinder is moving at certain velocity, so means that the velocity profile will become like this. Okay, you could imagine that. Okay, this is the moving cylinder. So then molecule here, okay, you will have a molecule here, then it will have this kind of velocity distribution. So this velocity distribution is in linear version. So means it is just a straight line. So and then, however, in this question, they ask us to calculate whether it is no slip condition and with slip condition. So that is the idea of this question. So we go for the first to calculate with no slip condition here. So we calculate the shear stress. So the equation is mu du dy, and we substitute with this one because from the question we know that the velocity is v and the gap here is delta r. So we substitute the value. And then we must know that the resistance here, the resistance that occur on this surface will be balanced by the weight. So means that we could say that the weight here is equal to mg, and weight is a force. So and then, so this force will be equalized with the force that comes from the shear stress from the molecule here. So how to calculate the force by the shear stress? So we multiply the value of shear stress here with this area. And this area is the area of the cylinder. You must get alert that you need to calculate the shear stress with the area of the moving parts. So we get the area here is 2 pi RL. So this R is actually the radius of this cylinder. Because for this one, might be you could assume that you need to use the value of R, but if you have a lot of parameter, for example, you have R1, R2, and so on and so forth, so might be you confuse which radius you need to use. So the idea is the shear stress need to be multiplied with the area of moving parts. So we take the R here. That's why we calculate the area here as 2 pi R and L. So this is an L because only the length of L here will create a gap here, and because we have a narrow gap here, the shear stress will affect greatly. So and then here we already calculate the we derive the equation for the shear stress of the moving wall with oh, wait a minute. Okay, so I'm sorry, this is for sleep condition, I think. Okay, for sleep condition. So, and then we calculate the shear stress here previously from question 1.16. So we just substitute the value of tau here, and then we could we could get the velocity, the cylinders falling into the hollow cylinder by using this uh, equation. So this, okay, I think I stop here. We go for the equation 1.21. So let's say we have an oxygen at 20 degrees Celsius and approximately it is around 1200 Pascal, ABS, absolute. So here, please be careful because in measuring pressure, we have two types of pressure, two type of measuring pressure, whether you present the value of pressure in gauge pressure or in absolute pressure. Yes,
Sir, can you please go back to the previous question?
yes,
Sir, in this question, I wanted to ask whether the cylinder that is falling through the concentric space, it is accelerating or not? Because when it will accelerate, the equation will change, right?
yeah. So
In the
normally, because this question, actually they want to get the terminal velocity. Okay, if you search about terminal velocity, we assume if the hollow cylinder is very long, and then finally when the you have something falling into that cylinder. So might be at the beginning they start to increase they start to have increment of velocity, but at one certain point after a certain time they will fall with a constant velocity. That's why we call it as a terminal velocity.
okay, sir. Okay,
Okay, okay. Try to search about the terminal velocity. That's the phenomenon that occur. That's why
okay,
if you jump from the space, okay, after certain time you will fall down with constant velocity. So that's the that one phenomenon in science we call it as a terminal velocity.
okay,
Okay.
sir. Thank you.
uh, okay. So for question 1.21, I think it's very straightforward. So we have a pressure of oxygen, the temperature of oxygen flow through a 35 micrometer diameter smooth capillary tube at an average velocity of 10 centimeter per second. So estimate the Knudsen number of the flow and whether slip flow will be important. So
Sorry, sir.
yes,
So you are explaining about the difference between absolute pressure and
okay.
this. Yes, you are explaining about that before you go to that question.
Okay, so okay, in this question, so we have a 1,200 Pascal absolute. So first, you need very careful because in fluid mechanics, there are there are two types of representing pressure. One we call it as gauge pressure, and one we call it as absolute pressure. So gauge pressure means uh, you are calculating pressure uh, from the atmospheric pressure as a datum, as your reference points. That is gauge pressure. Okay, but for absolute pressure, you are measuring pressure and you represent the value of that pressure by taking the absolute vacuum, means the real vacuum in the universe, not vacuum in this world, the vacuum outside the atmospheric as your reference points. That's why we could say that the atmospheric pressure is around 101.3 kilopascal. Okay, that's because because the difference of atmospheric pressure and the pressure at the in the space. Okay, pressure in the space is zero, and the atmospheric pressure in at the world at the Earth on the Earth is 101.3 kilopascal. Okay, means that the atmospheric pressure on Earth has a value. However, because we are living in this world, so the pressure inside our body is 101.3 kilopascal, so mean we are not feeling that pressure anymore. So that's why in gauge pressure, we could say that atmospheric pressure is actually equal to zero. Why we say it is equal to zero? Because it is not because it don't have any value. It is because we do not feel that pressure, and that pressure also not affects us. That's the difference between absolute pressure and gauge pressure. So to different the numbers, the value of pressure, for absolute pressure, so we use bracket ABS. So here, if you have 1200 Pascal ABS, so mean is it is actually lower than the atmospheric pressure. So mean it is in quite quite some kind of a little bit vacuum in on the earth. Okay, so this is the idea. You could search about the gauge pressure and the absolute pressure, because this is very important, because in certain condition they will give you a bracket ABS, so you need to alert that that pressure is actually the absolute pressure. So and then okay, for answer this one, I think you could go for nuts and numbers and everything, because it is some kind of dimensionless parameter, as I said in the beginning of our class. So in master's level, you need to be alert. There is a lot of parameter, dimensionless parameter that can be used in your research later on. So because we are dealing with oxygen alone, not the air, not the atmospheric gas. So because we are dealing with gas, so might be we need to use the idea of ideal gas here. So we need to calculate the value of R. As I said, the value of R here is not 287, because 287 is actually the specific gas constant for atmospheric gas. Okay, for oxygen alone, so because the molecular weight is 32, so we need to calculate by using this equation, 8,314 over 32, and you will get it is around 260. So, and then from the common table of oxygen, we could get at 20 degrees Celsius, the dynamic viscosity is 20 times 10 by the power of 6 kilogram per meter second. So, and then we could estimate the density is 0.0158 kilogram per meter cube. So, and then so we could calculate the speed of sound, which is A. So this is a very common one because for UTM graduate student, we learned about the compressible flow previously in our undergraduate. So this kind of equation is quite common. So we have the speed of sound here. So it's square root KRT. So, and then for K also here, you need to very specific. K is specific numbers for certain gases. So you need to find what is the specific number for this oxygen. So it is 1.4. And sometimes this number is quite same with other gas. For example, 1.4 also used in atmospheric gas. So I mean if you are dealing with air on this earth, so the value of K is 1.4, but the value of R for atmospheric gas is 287. And for oxygen, the K is 1.4, same with the atmospheric gas, so the air, but the value of R is different. It is 260 because the molecular weight of oxygen is 32. So, and then the value of mean free path is actually depend on this equation. You could calculate this one, and then you will get this value, 5.78 times 10 by the power of minus 6 meters. And then the Knudsen number is L over T, the mean free path over the diameter, and you could get that Knudsen number is 0.165, and then from this one, you could see the range. So if the Knudsen number is greater than 0.01, so mean the slip flow will be important. So, but if the less 0.01, so we find that it is not affected the flow.